Hello everyone and welcome to this module on Introduction to Continuum Mechanics. So basically this module is about the principle of linear momentum or equation of motion, or simply Newton's second law. And we're going to derive this equation here. So for this, suppose that you have a continuum like this, and this continuum is basically under some surface forces in here. So we show them using this T. So we have the stress vector or traction in here. And we also have some body forces applied to this continuum in here. So if I just take out an element from this continuum, and by continuum, you know that I am talking about you know an element which is basically surrounded by an infinite number of other elements. So if I take out this element in here and I show it here, so I have my right hand basis. So I have x1, x2, and then x3. And of course, this is very small. So this is delta x1, delta x2, sorry, this is delta, no, it's true, it's delta x2, and this is delta x3. And let me just draw these hidden lines with dash line. All right, so then we have attraction applied to this element here, which we call TE1 minus, because it's on the negative side of x1. And it is x1, x2, x3 here. It is a function of x1, x2, and x3. And here we have that TE1 on the coordinate x1 plus delta x1, x2, and x3 are constant. Then on this side we have TE2. So we have x1, then we have x2 plus delta x2 and x3. And on this side, I use this dash line here to indicate that this is on this plane. So we have TE2 minus x1, x2, and then we have x3. So then we have this TE3, which is a function of x1, x2, and then x3 plus delta x3. And on this side, we have TE3 minus x1, x2, and x3. So here we're going, and we also have this body force in here. So if I say that this is the center of the element, for example, so a volumetric force or body force we call is applied in here. So we show this with capital B, as the book also use this notation here. So according to the principle of linear momentum, the sum of the applied forces, including surface forces here like the tractions, and also volumetric forces. So this volumetric force or body forces, they can be like weight, electromagnetic fields, and these are equal to linear momentum, sorry, to the rate of linear momentum. So if we say, for example, the sum of t plus the sum of b is equal to the rate of mv, this is the linear momentum, and this is the rate with the time. And since m is not a function of time, so this one becomes here m dv over dt, which is basically a, or the acceleration. So this is the principle of linear momentum. So here I'm going to just sum all these forces in here, sum all of the forces in here, plus this body force, and equal it to ma, mass times acceleration. So we know that T, where we know this is as, which we know this as traction or stress vector, is basically the force per unit area. So here we have, if we want to define this TE1, for example, we have to write this TE1 x1 plus delta x1 plus x2, sorry, x2 and then x3. So now we have this force per unit area, and we have to multiply this by unit area to find the force. So here is the area that T1 is applied on. So we have the product of del x2 and del x3. So times delta x2 and delta x3, plus on this side we have Te1 minus x1, x2, and x3 times delta x2, delta x3. Then plus Te2 x, so Te2 is x1, this expression, x1 delta x2 plus, x2 plus delta x2, and then x3, and then the area is this one. So we have the delta x1, delta x3, delta x1, delta x3 plus Te2 minus x1, x2, x3, delta x1, delta x3. And I also write this for Te3. So I have x1, x2, and then delta, it is x3 plus delta x3. So it is applied on, let's say, delta x1, delta x2. So delta x1, delta x2 plus Te3 minus x1, x2, x3, delta x1, delta x2. And now we have the sum of the forces in here. And then we have to find this B here. So the book actually defined this B as the weight per unit mass. So some of the books basically use the weight per unit volume. So in order to find this, the weight, to get the weight force out of this, so you know that we have mg as the force from classical mechanics, and this m is rho v, where v here is the volume, and then we have g. So since this is per unit mass, so we have to basically normalize this with the mass to get the weight. So that's why we write this as rho v g, and this v is the product of delta x1, delta x2, and delta x3, and we keep this rho in here. So let me also change this color purple so you can identify this. So plus rho b, and remember this is per unit mass, is equal to, here we have rho a, or ma. And sorry, I forgot to put delta x1, delta x2, and delta x3, which is the, let's say, the mass. So basically, this is mass, m, b, and this is, for example, let's say that this is kilogram, this is b is, for example, Newton per kilogram, and then we can cancel out these two and then get the weight, or be out of this. That's why we use this notation in here. So this is rho again. Is equal to MA. So instead of M, we use rho delta x1, delta x2, delta x3, and then we have A in here. All right, so here we have TE1 minus, and we know that TE1 minus x1, x2, and x3 is basically equal to minus TE1, x1, x2, and x3. So we already know this from the previous modules. And we can do the same also for TE1, but TE2 minus and TE3 minus. Therefore, let me just copy this one. So, all right. So then I can change this to minus, get rid of this minus sign here. Then we have this minus in here. All right, so if you also notice that this is not going to be equal to 0, so it's not equal to 0, so we can divide both sides by this parameter in here. And if we divide this, then we end up with something like so here we end up with a minus delta x1. So 1 divided by delta x1, 1 divided by delta x1. This becomes 1 divided by delta x2, 1 divided by delta x2, 1 divided by delta x3, and then 1 divided by delta x3. And here we can write this as rho A, and this is rho B is equal to rho A. So if you notice here, this expression, so if I take this out, and I just rewrite this, so I use another color. So I also shift this a bit in here, and also shift this up, divided by delta x1. So if you notice here, this is the definition of the derivative. So it's basically fx plus delta x minus fx divided by delta x. So if we take the limit as delta x goes to 0, and here we have the same situation. So delta x1, delta x2, and delta x3, they go to 0, since we are just talking about everything in its limits. Therefore, we can replace this with its derivative. So basically we can write the derivative of TE1 with respect to x1. And since here we have x1, x2, and x3, so we have a multivariable function. So we have the partial derivative of TE1 with respect to x1. And this is, so if we do the same for delta x2 and delta x3, then we can write this as partial derivative of TE1 with respect to x1 plus partial derivative of TE2 with respect to x2 plus partial derivative of T3 with respect to x3 plus rho B is equal to rho A. Or if I write this in indicial notation, so we have a vector in here, so we have rho TEI with respect to xi plus rho BI is equal to rho AI. All right. So if you remember, we actually wrote this Ti equal to TEI. So this is basically the traction vector, sorry, the stress vector or traction, which we actually wrote as T JIEJ from very few, very first modules. So we had this transformation in here. So if I replace this into this equation, then I have T E J I E J partial with respect to xi plus rho bi is equal to rho ai. So this one, if I write it down, so I have the partial derivative of t ji with respect to xi ej plus t ji partial derivative of ej with respect to xi. And this is basically 0 since this is constant value. So plus rho bi is equal to rho ai since these are the unit uh, bases. So what we finally get is the partial derivative of t j I x I e j plus rho. And here, since we have ej, then we have to also change this to j. So bj ej plus rho, oh sorry, equal to rho ai, sorry, aj ej. And this is the final equation, or we call this the equation of motion. So if we take everything to one side, so then we have the partial derivative of t ji with respect to xi plus rho bj is equal to a rho a j. So I mean, here we have this in here, and then ej is equal to 0, then this is going to be 0. So the final equation is this. Or we can just swap I and j and finally write this is t partial derivative of tij with respect to j, and here we have I, and then we also have here I. Right, so this is the equation of motion. Or the principle of linear momentum. And there's also an an alternative to this, which is basically partial derivative of t ij with respect to xj plus rho bi is equal to 0. And this is for the static equilibrium. So we have this equation when there is no acceleration or any motion here. So basically this equation here, this overall equation here, it characterizes the deformation, the motion which is happening in each let's say particle or element of this continuum. So as it deforms, we can, as this basically this potato shape or this continuum is basically deforming, so we can characterize its deformation using these equations in here. Those, the book also put forward another topic on the boundary condition, which I would like to mention here. So you might have come across this this term in here, boundary condition, or B dot C, in many books. And this is basically this basically can be explained via a continuum like this potato shape that we have. So we apply some of the forces, we have some forces or traction forces on, let's say, on the surface. This is usually showed by gamma, small gamma. So the boundaries are shown with gamma, and there's some, displacement. And let's say we show this by gamma u, and this by gamma t. We have some tractions in here with a bar, the u's, or without a bar. Here we also have some uh, displacement boundary conditions on the surface, and we also have a domain within this surface or this volume, and we also have some body forces. So basically this small gamma is the boundary or on the surface of the continuum, and everything inside it is this capital gamma, and we use the body forces on all the capital gamma domain. We also refer to this traction as the natural boundary condition, and I use BC to indicate that this is the this is the boundary condition. And we also know this as, let's say, essential or geometrical boundary conditions. So basically, we have like the boundary. Let's say that this is your boundary. And on this boundary, you already know what is the normal vector and what is your traction. And using the equation of motion, you can find your traction, t, and you also know what is your normal vector. So you are able to find t, capital T here, or the stress tensor on the boundary. We also have another concept which we refer to as free surface. So basically, a free surface is a surface where the traction or the force vector is equal to 0. Here I use this to indicate that this is a vector. So it's like 0, 0, 0 in here. And you have to differentiate between a stress vector or traction and a stress tensor. So if you have a free surface, it doesn't mean that you have basically all the stress components are 0. So for example, if you have something like, let's say 0, 0, 0 here, because I want to get everything 0. So I have 1, 0, 0 in here, and then 0, 0, because this is going to be symmetric. So T2, 2, 3, 3, and even T2, 3. So if we calculate, if we find this t in here, so this gets 0, 0, and then 0. So you see that here we have a free surface, but it doesn't mean that your t, your stress tensor is equal to 0. So that's why I also mentioned that you have to differentiate between the stress vector and the stress tensor. These are not equal and they do not represent the same quantity. All right, so this recaps this module.